Hello, welcome back to the next tutorial of the subject VLSI Laboratory 21 ECL 66. So we completed part A in the last session. Now we are looking for part B, which is ASIC analog design. So in this, let us take the first one, 5th A, capture schematic of CMOS inverter with load capacitance 0.1. Set the widths of Wn equals to Wp, Wn equals to 2 times Wp, Wn equals to Wp by 2, and let's go ahead and do it. So earlier I have shared a folder, maybe a zip folder, something like this, microwind GCE. Extract it. Once you extract, you will get these two folders. So in that you go to system, then you will get this DSCH2 or 3, whichever I have shared with you. So you can double click on it, or you can make a shortcut to your desktop. This I already told you during the online lecture, and this, just by doing this, it will create a desktop icon, shortcut icon for easy usage. Do the same thing for microwind as well. Search executable file .exe. These are all examples that are made. There are many examples that are already been created, you can see. Okay, so this includes NAND 2, NAND 3 and many more. So at this point I don't want to look into these examples. Just do the same thing for shortcut creation. You send it to desktop, okay, so that you can access this software easily. There is no installation for this. Now I have the shortcuts already with me. We will start and do the experiment directly. So I just opened schematics. So what exactly they are asking you to do, I'll explain you. So you are supposed to do this, but you may not be able to see the accuracy in the results because this DSCH is not so sensitive enough to pick up the differences. Okay, so first I think we have to select the foundry. Okay, let it be default. That is 120 nanometer, but at this point we are not worried about the foundry. We can go for 180, 120 or 90 nanometer. So all these things can be taken care during the layout procedure, not here. So we are not so much worried. We are worried about only the three cases, Wn equal to Wp. So in this case, this is Wn. This Wp must be 2 micron. This is what the case. Okay. So now Wn equals to Wp. Let's go ahead and do the wiring. Do the connection. And give input. Either clock or push button is also okay for primitive experiments like this. Go ahead and connect. So this is about inverter. If you want, you can just check whether it's working or not. These are the waveforms, just now what we did. So this is inverter for you. That's not the intention of the project. The intention of the project is to find the minimum or find the best geometry. Okay, the agenda of the project is to do this best geometry, which is good. Whether Wn equals to Wp is good, or Wn equals to 2Wp is good, or like that. You just have to come up with the solution. That is what the intention of the project. Let's copy this and paste it here, and we'll try to rename this as clock 2. We'll keep the same thing. Have to put this ground. So you can check whether these things are connected or not using electrical connection. I feel there's a doubt here, so I can use this icon, view electrical net. So this is not connected to 0, this 0.3, so I should be careful about it. And then I have to take a wire and connect. So always place in with a distance and connect it with wire. That would be good. Now this is 0 and 0. So just so the second one what they are mentioning is Wn equals to 2 times Wp. So here I have to make 4 micron. Fine. Next one is, we'll say view all, and we'll try to do the same thing. Select. Copy it and paste it. So my mouse is not coming. So what I do, I'll paste it somewhere here better. And view all. If you click on all, everything will come. So from this point I'll take it down. Sorry, I have to move. So this is move. Okay. That was copy earlier. So from palette I'll take clock again. So just do these things again and again, you will be good at this simple software. And then the third case is Wn equals to half of Wp. So let's make it as 1 micron. Say OK. This is about the setup, what we are expecting. You can give it as out 2. This is out 3, the third case. Fine. And if I run, I should be able to see it in the waveforms. Okay. I think the frequency of this has increased. We are not interested in frequency, but anyhow I can make it 2 times slow faster, and I can get the same simulation. Pause and see the waveforms. Unfortunately we are unable to see the difference very much clearly, because as I already told, it is very much primitive software. We will be identifying the differences of rise and fall time in the microwind after doing the layout. Okay, let's go ahead and do the layout for this. We'll keep this for as a reference view all, so that we can see optimized one. What best can be done is we do not have foundry at this point. Okay, let's go and do microwind layout. So there are already videos that I have shared. How can you generate your own device, but at this point I'll just check which foundry is there. Select foundry. So earlier we have taken 120 nanometer foundry, so we'll stick to that, or we can stick to any of it, nothing wrong. 120 nanometer also is okay, or you can go to 90 nanometer, that is also good. Okay, 120 is fine. Open. Now as soon as you do that, it will show design rules, what is minimum, what is maximum, and everything. Okay, now let's go ahead and take PMOS. Minimum is 0.6 micron. So what I do, I'll check for this as well. So what is the minimum? 0.6. Keep that in mind. 0.6 micron is minimum for N and P. So what is the minimum of WN? In this case it is half of this. What is minimum of WP? So 0.6, which is not possible. Okay, which is not possible. So if I take 0.3, it may give some error, or it may work. I don't think it is not going to work. If I say take 0.3, let me check and put it here. If I say DRC, okay, I think it works, nothing wrong in it. So what I do, I'll go with minimum. PMOS 0.6. The first case is 2 micron, and here it is 0.12. okay, 0.12. So the first case is 2 micron by 2 micron, or we'll stick to the minimum. Even we can go for 2 micron. 2 micron, you will understand how big it is. If I try to generate, view all, this is how much it is. Nothing wrong. We'll go ahead and continue with the design. 2 micron. NMOS also 2 micron. So it is adjusting its width. Generate device. We'll keep it very close to this so that you'll understand what we are trying. I think I just clicked on that, edit, undo, view all. Okay, everything went now, nothing is there. This is the primitive software, as I already told. 2 micron PMOS, 2 micron NMOS. The first case, I'll keep it here, then I'll try to connect. Then I'll move it. Okay, I'm moving it so that I can keep very aligned. So I'm not worried about the area at this point. If you see okay, let me go ahead and do DRC, design rule check. If I do some mistakes, it will give design violation or DRC errors. What is my intention is to connect without much effort. I want to minimize this video. I'll try to make it as short as possible. Suppose if you see, okay, I think I made a mistake here. Okay, see, if you see the schematic, the source is connected to VDD. Here the source is connected to ground. Only gates are connected common, and these drain and drain are connected common. So this drain and drain connected now. I'll try to give source to VDD. I can take metal one and draw it, extend this to a little bit more, give VDD, and also give VDD to N well. These are the aspects that are covered already in theory, so I don't want to explain you about this very much. Now I am trying to give ground as well. So the connections are made. Now I have to give input and check the output. Give clock as say in, and did they give any specification about inputs and outputs? Yeah, they have specific input. Rise time 1 nanosecond, pulse width is 10 nano, fall time and rise time are 1 nanosecond, and period is 20 nanosecond. Okay, let's go ahead and do it. Low to high 1 nanosecond. This is TL 10 nanosecond. The rise time low to high is 1 nanosecond. This is what they mentioned, so we are sticking it to the experiment. High to low is 10 nanosecond, that is high value is 10 nanosecond, low value is 10 nanosecond, that means total width is 20 nanosecond, that is total period is 20 nanosecond. This also they mentioned it as 1 nanosecond. So this create your input. Also we would like to see output. You take a visible node from the palette and keep it here. So this is out for you. Assign. So this is the inverter, first one. If you just want to check whether it is working or not, and just simply run. I think the period itself is 20. So if I want to simulate for 2 cycles, I need at least 50 nanoseconds. Simply go ahead and reset. Yeah. If you see, this is high, this is low. You may not be able to see very clearly because the color of this background is black. If I try to change the color, simply print it. I have some different printers, or simply take a print screen and invert it in paint. Okay, let's try to do this. I have a printer. I'll try to do it in the printer. Okay, it is printing the schematic, printing the layout, not the waveform. So click on more, close, run again. I'll take screenshot from keyboard. I'm just pressing that print screen button in the keyboard. Go to paint, Ctrl V, that is paste, and invert color. Right click on that, invert color. So you could able to see this is logic 1. It is going low, coming high, going low, and the same thing is happening for output as well when input is 0. So the input is 0 here, output is high. So you can able to see it is logic 0. It is logic 0 here, so it is logic 1. So this is all about first thing. Okay. Now we may not be able to get this rise and fall time because it is too high. We have to make it more precise. So still it is not possible. So I think we should give very high or fast input so that we can able to see it. Let's go ahead and make it faster. Assign and run. Now you may able to see. Okay, I'll try to make it less. The rise and fall. Okay, even you am unable to see the fall because it is too big transistor. So we have to make it still faster. So just take 2 nanoseconds, reset. So you could able to observe rise and fall. My intention is to take this 5 picosecond and 1 picosecond. We'll try to tabulate it a bit later. It's okay. Now we'll get back to the another part, that is what is it? Second one. What is it? 2 micron by 4 micron. Go for palette. PMOS we want 2 micron. The minimum is 0.6. What it is 0.3 also is okay. What it is recommending. So let's generate this. Keep it this PMOS as it is. We can even merge it with all other. That is also okay. But you can keep it separate, nothing wrong in keeping separate. We are trying to move it. Fine, and let's check for any DRC errors. Next, the case is 4 micron. So we have to go for 4 micrometer. NMOS, generate, keep it here. This is a bit bigger now. What can be done? We can take finger, nothing wrong in it, but I don't want to complicate it. 1A, let it become simple. What I am trying now is edit, undo, move it. We are trying to move this transistor down, and we'll try to keep it aligned with this so that we can connect it easily. Okay, so if I zoom it, it's not in align with the PMOS. What I'm trying to do is taking a bit left side. This all comes by a bit of hands-on experience on this. Okay, so let's check DRC. No, there are no DRC. I am zooming it to a particular part. Can I connect or not? That is what the okay, it is in a line. We will go ahead and connect VDD and ground. This is VDD, and one more VDD we require for this PMOS. We can connect all these things and we can shorten, we can give single VDD. And also input can be same. If you try to put it together, inputs can be connected, or else what will happen? Okay, that is also a problem. You will get too many inputs and too many outputs on micro output window. That's all okay. Let's keep it simple and note it down one by one. It is also going to be simple, or you can compare it directly there itself. Let's move these things together so that I can connect common input, or we can merge it, nothing wrong. Let's merge with this, check for DRC, no DRC errors. So I can give the same input here by taking poly. I should not take it. I have to take a contact with metal one, and I have to, but for simplicity at this point I am doing it. Take polysilicon and give common input. Okay, just check for DRC, no errors, and output should be different, should not be connected common. VDD can be common, so I'll try to make it common, or I can make a common metal for this. Check for DRC errors. Next one, what I have to make? So I have given same input. I have to take output with a visible node, that is out to second case. Also I have to connect ground. I can short these two. Anyhow, it is too far away from this point. I don't want to waste the metal. I'll simply connect another ground. All. So two cases are ready now. These two cases. Let me run. Okay. If I run, I should get out 1 and out 2. Okay. Here it is, rise and fall time for you people. With respect to in, out 1 is how much you can able to calculate. It is 7 picosecond and 2 picosecond. With respect to out 2, you can also calculate the same thing, 9 picosecond and 1 picosecond. Roughly it is 8 picosecond, here it is 2 picosecond. We'll take any one of this. Over the period of time it has become negligible, so it is roughly I can take it as 1 picosecond. So I'll explain what exactly we are trying to do in this now, after doing one more layout part. So let's do that. Go to palette. The third case is 2 micron by 1 micron. Let's go to palette. Take PMOS. How much? 2 micron. Okay. And take NMOS. How much? 1 micron. Generate. Keep it here. View all. So I'm trying to move this, and since we are giving common input, we are trying to connect along with it. Suppose if you don't connect properly, it may give DRC error. Just now if I just placed, can you see there is a gap here? So this may give DRC error. Yes, it's giving the spacing between N1 is less than 11 lambda. So what I have to do, I have to take it again and correctly I have to paste it. Okay, now there must not be any DRC error. View all. So I have to take this and keep it very close to this. So I am not worried about area, so I am very much interested in demonstrating the intention of the project. It's all about sizing. So let's go ahead and zoom. Can I able to connect these two now without much effort? Yes. Fine. So I am also taking polysilicon 1 and trying to connect this with this as well. Check for DRC errors and give it as output 3, case number 3. Assign and also give VDD and ground. This must be ground. Okay, and connect this to common VDD. Metal 1. Edit, undo, take metal 1. Check for DRC errors every time. So it is also VDD, and this well anyhow it is already VDD, but I can able to ensure that there is one more VDD there. Okay. So input is same, outputs are different. Let's go ahead and run. You can able to observe case 1, case 2, case 3. So what we are observing, let me increase this a bit. If I try to do this, so it is over the period of time it is settling, so let it be somewhere around 500 picosecond. Okay, but unable to see rise and fall. So what I do, I'll increase the clock bit. Okay, bit slower. Assign, run. Okay, this is a bit better. If I take with respect to out, so 4 picosecond, it's only showing one thing, not the other one, but I can able to see it here. It is 3 and 5. Fall time is not visible, so I want to adjust the input so that it can give both rise and fall. So let me increase this first. Further. So what I do, I'll just pause this video and do trial. I'll do trial and error. I'll get back to you with correct. Okay, I'm trying to adjust this input to the given values in the syllabus, what they mentioned in the syllabus. Rise and fall as 1 nano and pulse width 10 nano and total period 20 nano. So go back and trying to adjust the same thing. 10 nano low period, high, that is pulse width 10 nano, and overall period will be 20 nanosecond. So it is 10 plus 10 nanosecond, rise time 1 nanosecond and fall time 1 nanosecond. We'll keep the same thing and we will try to adjust the output in the output window itself. Okay, let's go ahead and run. We have three different inputs where WP, what are three conditions? So equal 2 micron, 2 micron, and we'll try to see it. With respect to this, we are supposed to find TPHL, TPLH for all geometrical values. So what we are supposed to do is go and tabulate for this. Okay. We'll try to have these 3-4 cases. Okay. WP equals to WN. What is TPHL? Small t, capital P, HL. High to low. TPLH. Low to high. TPD is, you can take average of this, or there are other ways to calculate. We are very much interested in this now. So we will try to tabulate. So adjust, we are trying to calculate the low to high of in with respect to out. So in is a reference, out we are taking the first case WN equals to WP, and you keep it for 100 nanosecond. So that will get 5 cycles and simply hit reset. We are trying to take the values which are common. You can see rise time, it is TPLH, it is 320 picosecond. TPLH 320 picosecond. And TPHL high to low, it is repeated values are 160 picosecond. So sometimes you may not be able to see these values, so you have to adjust these steps. So I have adjusted it to 40 picosecond. By default it may not be 40. So I have taken it for 100 nanosecond so that I can see 5 cycles. You can do more and more, and you can do reset, all those things you can do. So twice it is repeated, so I would like to take this 160 picosecond. Next one, WP, sorry, I forgot. WN is 2 times, okay, as given in the syllabus. WN, you can mention WN equals to 2 times WP. N first as given in the syllabus, copy, equals to WP 2 times WP. So we are trying to do this, just select it with auto to, simply reset. So we are getting these rise and fall. Rise TPLH, it is nearly same, it is 360 or 400. Fall is 160 picosecond. It is about 400 pico, low to high. But fall has reduced because we have increased this size, no? About 120 picosecond. Okay, 120 is repeated, only 160 somewhere here, because suppose if I try to do 20, you may get better, but I don't want to take this and confuse you. So here it's showing only rise, so we don't want this it's a primitive software. I just wanted to take everything in consideration. So 120 is common, many times it is repeated. You can see 120, 120, 120. Somewhere we got 160. We are taking the values which are common, 120 picoseconds. Next case is Wn equals to Wp by 2. Okay. So let's go ahead and do the simulation with respect to 3 and simply hit reset. Now we got an optimal one where it shows nearly it is same, 200 and 240, which is very close. If you try to increase this, and you may get better, but we are not interested in that, so let's do it with 40 only. So it is nearly close. 240 is rising, rising to 40 picosecond. Falling is also 200 picosecond. So even if you average it, okay, so in this case, where Wp equals to 2 times Wn, or Wn equals to half of this case, is giving optimal solution. Okay, you have to highlight this and you have to make a comment for it here. After doing this, you can calculate TPD. Okay, TPLH. TPD is not, TD. TD is there. You mention TD, you calculate and mention TD and enter the values here, and you can conclude that, give a conclusion. Saying, okay, case number 3, Wn equals to Wp by 2 or Wp equals to 2 times Wn is giving optimal delay or equal rise and fall delay. So this is your conclusion. This must be your conclusion. Just to do this, just to give an idea about this, they have kept this equal rise and fall delay. You can mention. Suppose if you do it the different rise and with faster clock, you may get it better, but at this point we are sticking to what is given in the syllabus. Next one, what we should do is we can what else is given, what they are asking you to find. Okay, part B we'll do it bit later. Delay and best geometry, so you write it as best geometry. Therefore case 3 is best geometry, something like that you write. Okay, this is all about this experiment. See you in the next video.